I think most of y'all know who I am from physics last year, and then things of that nature. So I have been asked to come talk about batteries, and so specifically a lithium-ion battery, because one of your projects is to help model the degradation of these batteries. I mean, something that we use, and so you've got lots of data that talk about, that should at least speak to the catastrophic failure to just general failure of these batteries. But I was asked to kind of talk about what is really going on with these batteries chemically in the first place. So one of the questions that's always worth asking is, what do we even use these for? Like, why do we need a lithium-ion battery? And so one of the big points of the lithium-ion battery is that their range of use is incredibly broad. From general transportation, if you so choose. Storage is a big world that batteries are working in right now. I mean, we've got wind, so being able to store that energy. We can stick all these windmills out in the middle of the Midwest and we can collect energy, but we may not need it immediately. So we've got to be able to put it somewhere. And so batteries are a big idea. Can we charge a battery using this to then utilize the energy later? Electric transportation, not just at the personal level or individual, but consumer or commercial level. Can we use these batteries to help drive that? Again, solar charging, same idea as the wind. We've got sunlight for, depending on where you live, we can gather this energy. It may be during a time that it's not needed. And then we need energy at night when there's no sun. So can we store this energy in such a way that it's utilized at a later date, later time? Electric vehicles, consumer electronics, charging stations in general. So this whole world of batteries is pretty important. It gives us the ability to portably take energy with us. And so again, we use this every day. Most of you probably have one in your pocket with the iPhone or things of that nature. Surely no one has Android, right? Okay. Well, I'll have to skip a couple of slides then. So the big question, why lithium ion? Anybody know? Why do we use these? Why not just buy a bunch of double A's? Lithium is cheap, it's rechargeable. It's like you knew what my next point was. Absolutely. One of the great things about lithium-ion batteries is they're rechargeable. So in a world that is conscientious about waste, it's conscientious about space, we don't want to fill up landfills with batteries, specifically lead-acid batteries or alkaline batteries. Those are metals, those are things that we don't want just laying around. We actually have an entire bin that's about half the size of this podium in our physics storage room full of batteries that are no good. And so this is a huge reason behind the lithium-ion battery. They're rechargeable. And so we can use these over and over and over again and create less waste. Other reasons, what do y'all know about them? They're very efficient for their size. So comparatively, their size, they have a very light weight compared to all these other batteries. Again, lithium being much further up, just like this periodic table to my left. Lithium is a very lightweight metal. And so 3 protons, mass number about 7 roughly where you're at. And so it's light. And so it increases its application greatly. We can use this in a lot of, again, applications where weight would be a factor. And so that increases efficiency as well. The big one that we still work with is this idea of memory effects. So what do y'all know about memory effects? I mean, has this been something you're aware of when it comes to rechargeable batteries? Have y'all talked about that at all? No. Okay. So prior to the lithium-ion battery, some of the earlier technology that existed, the nickel-cadmium battery or even a nickel-like metal hydride battery, one of the issues with them is that they had memory effect. You had to fully discharge the battery. So when you would go place this on its charger and it needed 8 hours to charge, Once it was full, you had to use that to the very last drop. You needed to expend all of the energy that battery stored, and then you could recharge it. The memory effect is because if you didn't, the battery would learn how much its capacity was. And so if you only spent maybe 25% of the battery and thought, well, I'm done doing whatever it is that I'm doing, building a deck with a hand drill, or going only a couple of miles on your scooter, and then plugged it back in, it would only need to charge 25% because that's all that was left. Well, after several cycles of doing that, the battery would memorize that, oh, this is apparently all the capacity I really have is 25%. And so the battery would begin to learn that this is only the amount of energy I had. So while I may use 25%, at that point the battery would say, I'm done, go charge me again. So it's kind of learned that that's all it needs. The lithium-ion battery doesn't require this. It's built in such a way with that mechanism that if I only go a couple of miles, while it's a 15-mile range on my scooter, I can plug it in, there's no memory effect. And so this has been a huge leap forward in terms of batteries, just for the utilization of charging. We're not losing that idea in terms of how much memory, how much battery power the battery can hold. The big one outside of that kind of combines all of these ideas of efficiency and weight and memory loss. It's this idea of energy density. And so lithium, what do we know about lithium? Chemistry folks, maybe a couple of years. Solid at room temperature, okay. Alkali metal. How many valence electrons does it have? One. It's a group 1 alkali metal. So what do we know about its reactivity? High reactivity. And so we figured out how to utilize this idea with the alkali metal of lithium. It's safe enough to utilize, and we get roughly, they estimate about 150 watt hours per kilogram of lithium. If you go back to your old lead acid batteries, and some of you may have experienced this, 25 watt hours per kilogram. Lead acid batteries, what you find in your cars. Again, big battery, weighs a lot. It's got enough to start your car, and then you need an alternator to keep it going for the rest of the way. Even the older technology, but better than a lead acid battery, nickel metal hydride, 70 maybe to 100 watts per kilogram. But again, in terms of the energy density, significantly higher. And so that drives the idea of lightweight comparatively. It drives the fact that we don't need as much of it, so we can make smaller application. And it drives even, again, it drives all of these ideas of efficiency. So lots of reasons why lithium ions, why this is an important technology to continue to work towards and build out. Why not lithium-ion batteries? What's the big one? They explode. Yeah, well, that's kind of where we're headed in a lot of ways. What else? Do y'all know anything about the lithium-ion battery?
The rate at which they charge, it's asymptotic.
Yes. And so we've got degradation. The moment that battery leaves the factory in its fullest sense, it begins to degrade. And so even the best and brightest of our lithium-ion batteries, so to speak, probably 2 to 3 years shelf life. As you begin to use them, they degrade. Things chemically are being used, the electrolytes, the lithium, things of that nature that are on the inside, and we'll talk about that, but they degrade. And so charge rates change, capacity rates still change, and while we get incredibly high density on the front end, it's not a forever solution. Yeah, what else? What do you never want to do to a battery in general? Heat it up. Leave it out in the sun. Absolutely. And so, again, lithium, extremely reactive. Number one rule there is reactivity is driven a lot by temperature. And so these lithium-ion batteries are extremely temperature sensitive, to the point that it will significantly shorten their life. And so while the hope at all ideal situations, you can get 2 to 3 years out of one, store them well, store them wisely, because you can definitely lose out on many years and even many applications. I mean, mid using on a hot summer day, your drill will probably last a lot less than it would on a cooler day. Yeah.
Is that the temperature sensitivity? Is that like it shortens lifespan if you're like changing the temperature constantly? So like you go from cold to hot, or like so if say you're in a hot place all the time.
Yeah.
Would it be any?
Both come into play. I mean, so two different ideas there, yeah. And so they both play into this, that one, the extreme high temperature all the time is just naturally driving a higher kinetic rate. And so within the chemical reaction, it's going to happen. If you continue to then, cool it off, heat it up, cool it off, heat it off, that's doing another type of thermal degradation as well, but both will shorten the lifespan. And so, yes ma'am.
Is it just the heat that will shorten its lifespan, or also will cold weather affect it?
The cold will affect it as well, yeah. And so we'll get to those degradations here shortly about that. But yeah, it's one of those where there's an ideal range that these want to work and want to operate in. And so both can happen. If we too cold, let's kind of take a sidestep on that. When we look at electricity, that's what we're trying to gain out of these batteries. What is electricity in the most general sense? Flow of electrons. And so one, high temperatures increase this thermal kinetic rate. And so it creates the reaction. And so that's going to degrade some things. And it's going to happen. If we keep cooling this down though, what are we inadvertently doing? We're slowing down the flow of electrons. And part of the chemistry of these batteries is the natural ability for the electrons to flow in both directions. While in charge, to get from the anode to the cathode, in charging to get from the cathode back to the anode, or in discharge to go from the anode to the cathode. And so if we're extremely low temperatures, we're naturally inhibiting that to occur as well. So both come into play. Most often the catastrophic failures are a high temperature. So yeah, good question. What else do y'all know about what makes these bad? Don't know. Unknown. Yeah, what were you gonna say? Yep. Well, some of them are thin. In fact, though, a lot of the weight in a lithium-ion battery, in most applications, is actually the housing to keep all of this stuff in here. But again, we then try to make the right materials to keep it light and things of that nature. So sometimes light material may be easily penetrable. So we'll talk about it. Part of the lithium-ion, one of the issues with them is they can be ruined. You can fully, again, part of the chemistry makeup is the ability for the lithium salts to move back and forth through a separator. We'll look at the chemistry, and to allow the electrons to flow. If we completely discharge the battery, typically below a volt or so, the electron, or more the lithium salts, will localize themselves into a singular place with no ability to then get back to the other side. And so we can ruin these quite easily at times by completely discharging the battery. And so while, again, old technology said, move it all the way down, use every last drop of it, and then charge it back up to full, there's actually practice within the lithium-ion battery to not necessarily do that. You don't want to just run it out. They are expensive, not because of the lithium, but because in a lot of ways computers help regulate this idea. Again, take my scooter for instance. I plug it in, it takes about 3 hours to charge. Do I want to just stand around for 3 hours and wait for this thing to charge? No. When do I most often charge this, would you think? At night, in my sleep. Yes, before I go to bed, I put it on the charge. I already kind of talked about what is charging doing. What are we doing to this thing? we're pumping in electrons from our house and we're moving the salts around. And so if I keep doing this over for 12 hours, but it only needed 3, what's going to happen? It's going to be unhappy. Catastrophic failure. So a lot of these batteries have some type of computer built into them to help regulate the charge or discharge, to help keep it from overcharging, to help keep it from over discharging, to give it a stopping point. So even again, those batteries that you get from Home Depot, they're so big because there's some computerized software and chips in there to help it. Hey, it can go this far and then it's done. Now it's not completely discharged, even though it won't run your drill anymore, but it's there. And then they're explosive. So lithium is highly reactive, and so it has, with water, lithium makes a nice kind of reactive explosion with water, which is fun. Go YouTube that. It's even better though once lithium, if lithium is exposed to heat in an extreme sense, aka fire, you have a runaway thermal reaction. I mean, it can get pretty violent. So not something you want necessarily in your pocket or on an airplane, things of that nature. So there's lots of reasons why not to lithium-ion batteries, which is part of, again, this project. Can we understand a lot of these ideas to help push us towards the direction of using them more? So how a battery works. In the most general sense, that's kind of what I think we were here for today, how this works. So we've got our cathode, our positively side, in general sense electrode. We have a cathode and electrode, or cathode and an anode. The reason how I kind of remember this is the cathode being positive charged, the positive side of things, because cats are positively evil. So, that's debatable. And so in that gives us the cathode is the positive charge. If we want to be nicer, cats have paws. There we go. So, but either way, the cathode being the positive side, and then the anode is the negative side, just because it's not the positive. So I don't have any mnemonic for that. But during charge and discharge, what's driving the electrons to give you your current is the movement of the lithium ion within the system. And so this should play. And so as we're charging our house, it drives the electric current in to bring all the lithium back towards the anode. And then once we dispense that, the lithium drives back to the positive side as the electrons flow through to light your light bulb or drive your scooter. And you can see how the energy and the charge density changes based on what we're doing. So again, anode oxidation is occurring. These electrons are moving out of the system from the electrolyte and the anode material. And they're going to produce, at the initial charge, we get around the anode what we call this SEI, so a thin film that forms around the anode. And so this, kind of, that's short for solid electrolyte interface. What's occurring there is the ability for ionic transport to occur, for this ion conductivity to occur between the anode and create oxidation. And that way, once things are oxidized, the electrons that are released in that can create your current. The cathode reduction. So again, we still have some compounds to form there through that again, through ionic transport, allow the motion of, again, electricity or electrons to occur both forward and backwards. So we want to discharge our energy. We want to be able to then recharge it as well. And so we need both sides to form these SEI layers in order to help promote ionic conductivity. And a lot of our degradation occurs because of these films either becoming too thick or degrading down and having a lot of byproducts. Other things within a typical battery. The electrolyte, so we've got just an electrolyte liquid. if you will, that allows the charge to flow within the battery. And so this is typically made up of some lithium salt. A typical one would be lithium hexaphosphate is pretty normal, along with then some aprotic solvent, some carbonate, something that doesn't act like water, which is important because what is highly reactive with water? Lithium, which is what the whole battery is. And so we need to make sure we've got something that allows for flow, a fluid that allows for flow that is not reactive with the lithium. I mean, then we've defeated the purpose, and we're just making bombs at that point instead of making batteries. And then the separator that isn't really shown on this screen. I've got a better picture of a lithium battery in the next screen. But a separator. So the main goal here is to keep the electrodes from actually touching. It's not something you want. You don't want to short circuit out your battery. So another huge issue within these things that cause for catastrophic failure. Short circuit. Anybody short circuited anything before? What's a main component or result of short circuiting? Sparks and very hot heat. And what are two issues that we need to avoid when it comes to lithium? Heat and fire. And so again, this plays a major role in terms of keeping a battery working well, and is part of the degradation issue. So in a more general sense, for a lithium-ion battery, here's more of what we're looking at. So our anode is probably some carbon-based anode. We've got lots of forms of that. And then our cathode, some lithium metal phosphate, maybe lithium oxide of some form. But it's something that allows for reduction and oxidation to occur on both sides. And I know that from the talk that was given it was a couple weeks ago at this point. I mean, what's one of the issues of the batteries losing power? And it's kind of being gleaned from this. It makes a lot of sense when you see a picture like this with these batteries. I know there's talk about something occurring to the lithium ions within the battery. At least Dr. Mimbs talked to me about it. They get stuck. They get stuck at one of the anodes. Yeah, and I think he talked about them getting stuck in these pores and these rigids. And that makes sense. I mean, especially over here at the cathode, I mean, you've got these chunks of phosphates and iron oxides, these very rigid materials, and you got lithium trying to make their way out. And so it's, at a molecular level, it's kind of easy to see that there's issues here. If this gets too complicated, if this gets too overgrown, stuff is not going to make it out, specifically the lithium. And so we've got to work on those things. So any questions about what's going on so far? No? So we've got our chemicals within the electrolyte, which is the lithium salts. We've got our anodes and our cathodes that are creating the reduction and the oxidation to allow for the electron flow to either discharge to create energy or to charge to store the energy. The issue is you've got data about things failing. Why do these explode? Why do these stop working? There's four big things chemically that occur. One, we can reduce the electrolyte because of something going wrong at the anode. And so again, I already talked about this. The anode, once it's initially charged, it forms this SEI layer, this solid electrolyte interface, that allows the lithium ions to then interact with the SEI layer and create oxidation. So the electrons then can form and create our energy, give us something to run our scooter off of, run our electric battery, whatever it is we're trying to run, light bulbs. It's an ionic conductor. I mean, that's the whole point, is we want to conduct these ions. What is interesting about it is it's pretty much, once it occurs on the initial level under initial conditions and kind of standard run-of-the-mill atmospheric pressure and temperatures and things of that nature, the film thickness is pretty constant. It acts as an insulator to keep this from growing, and it works. It doesn't get any thicker, it doesn't get any thinner, and it allows for the perfect rate of transfer of these electrons. What can happen with that is the thermal decomposition. We've got some real issues that if we raise the temperature, if it gets too hot, the reaction rate increases. And so we end up increasing the thickness of our SEI layer. So already thinking back to that other image of the battery, the goal of the SEI layer is for ionic conduction, to get ions where they need to go and get electrons where they need to go. If this thing suddenly grows and becomes a lot thicker, what happens? It's going to get thicker even faster. So we got some exponential rate there. What's happening to the ion transport? It's got longer to travel. So in terms of its transport rate, it's got to slow down. Or some could even argue, well, it's got to speed up. Well, what comes along with speed at a molecular level? Huh? Build up heat. And so again, what most, on the general sense though, is as this grows thicker, the lithium-ion transport limits, it gets inhibited by this. That limits charging because now I don't have all the lithium ions able to make it back to the other side when I charge. And so this is where this word comes in, impedance. I think he talked a lot about that. That's just the resistance of transport. And so impedance is the general word that we use for resistance. In DC, it can be used both for DC and AC. Resistance, oftentimes, I'm about to show that I have forgotten. So resistance is in the DC, so just direct current. Impedance allows us to have the magnitude and the phase angle that occurs in alternating current. And so where we don't have phase angle, its phase angle is 0. So we just say, what's the resistance in direct current? Well, it's whatever the light bulb is resisting. The AC, we have impedance because we also have phase angle. There's something there that plays a role in how far off we are as we do these things. And so if we increase impedance, we're increasing the resistance, things slow down, the battery can't hold the charge as long. And so we lose battery capacity. The other big side, if we're increasing heat, again, what comes along with heat? Eventually, even using some of the keywords. What's that? Movement. Fire. Yeah, all of those things. And if we go to Boyle's law, Charles' law, or whose law that relates temperature and pressure? Or we'll just use the ideal gas law. But specifically, who? Or is it Charles' law? So the ideal gas law, if temperature goes up, we're most likely also increasing pressure. And so again, catastrophic failure. The liquids with inside, even at the cathode, can degrade, and you're going to get some oxygen gas. I mean, you're just going to have pressure build up. Eventually, you're going to have an explosion. So heat, really bad. We don't want that to occur. And so that's one big realm of failure when it comes to these batteries, is what's happening at the anode. Also, just don't store it for a long time. If you just let it sit there, this is also going to happen. It's just going to build up because part of keeping this thickness at the right level is the transport of these ions back and forth. And so if you just put it on a battery, put it on the shelf and never use it, reaction will occur. And so one of the things to always check if you go to the Home Depots or the Lowe's and you need a new battery for your drill, make sure the manufacturing date is within, I would say, a couple of months. Otherwise, you're maybe getting a battery that's not going to last very long. Other things that can decompose due to heat, the electrolyte itself. And so the carbonate solvent, that's the big issue there. It's pretty volatile in the sense of heat. It doesn't take a lot. So these typically can decompose at 70 degrees C. And so again, if things are decomposing due to heat, what's building up? Most likely. Pressure. Dun, 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 dun. Yes. And so at that point, things also, the decomposition of these carbonate solvents, they begin to react with the electrolyte salts themselves. They will react with the lithium instead of the lithium ions getting to the anode or cathode. And so you've got new compounds just completely being formed within your battery, which then creates even more side reactions. And so you got major decomposition. The higher the rate, as everything increases, again, this just kind of becomes thermal runaway. And reactions occur that increase heat, increase pressure. More reactions occur, more things are made. And instead of actually getting electrons due to oxidation and reduction, we just get fire. And we get an explosion. And that's not what we want. So heat in general, if it never makes it to the anode part, it could just be the decomposition of the electrolyte itself, causing some issues. Two more big reasons or ideas behind this issues that we got. We can oxidize the electrolyte by the cathode. So as the cathode continues the reduction reaction, the electrolyte can get oxidized. So this happens, one, by overcharged storage. So again, we just leave this on the charger for too long. We don't have a computer that's going to help say, hey, you're at full capacity, stop. And so we just keep pumping in and pumping in. And so at that rate, we begin to form this SEI on the cathode. And so that occurs, and what then at that point happens? If we have new film thickness that's growing and growing, what gets inhibited? Same thing as the other side. We get ion transport, gets limited, lithium can't get where it needs to go, it insulates, it increases impedance, and it's going to try harder and harder and harder. You're going to have rate increases in terms of heat, pressure. One of the issues on this side is that you can even get uneven current distributions. Things don't discharge at a continuous rate. It can suddenly increase or decrease. And so we got issues there. So a lot of it's still chemically the same as happening, just on the other side of the battery. We can undercharge this thing, and so at that point the cathode isn't getting the movement of electrons. The electrolyte isn't being able to transfer the lithium back and forth at the rate it needs to, so the cathode material just starts to degrade in general. And so that lithium cobalt oxide, which is a really normal, the lithium iron oxide, begins to just degrade. It's not getting the oxidation reaction that it needs to occur. And so it just says, I'm done, and it's going to degrade. This is the big issue with this side, is that it will release oxygen. Because again, those are usually some type of metal oxide that is there, and so that oxygen release increases pressure. And if you have pressure within an enclosed space, explosion. And so this is bad because it's just irreversible capacity loss, AKA. If it doesn't get that far though, but even it's irreversible, you have degraded your cathode. You've degraded the material that's allowing the transport of ions. Short circuits. And so overcharging. So again, transport of electrons. If we overcharge this to the point where that we push all of the electrons as far as we can, that allows them to actually make them all the way back to the lithium ion. It will reduce the lithium ion. And so in that, we just get metal lithium. We get actual metal lithium buildup. And so one, if we've got an actual solid now showing up in our ionic liquid that we're using for electrolyte, that's bad. I mean, the lithium ion that was meant to be part of the transport equation is now no longer transporting anything. It's just a solid that exists. And so the bigger issue, though, is that I pointed to my screen on my computer, like you all could see what I pointed to. I do that a lot. The lithium, if it continues to build up, it's going to build up these dendrites. I mean, little branches. You may have seen pictures like that blown up on YouTube or the internet. But just it's going to build up little fingers of lithium that eventually can pierce the separator. And so that's a big issue at that point. The thing that is meant to keep short circuit, the electrodes apart from each other, is now broke, and those dendrites can move all the way over and actually create a complete circuit between the anode and the cathode. That's going to cause a lot of heat. That's going to build up a lot of pressure. That's going to cause a fire. That's going to blow up. And so this is a huge issue in terms of what may be going on with these batteries, is that we have some failure of the separator. We've done something to our battery. We've overcharged it. We've to where lithium is being produced and actually piercing the separator and creating an internal short circuit. The other side, and again, if a computer is not in place to keep this, if we over discharge, so one of the pieces of the battery, don't really talk about it, but there is a electron transfer kind of facilitator, a copper anode that exists that helps collect this current, helps facilitate transport. It's really not an issue unless we start over discharging our battery, because now we get a buildup of electrons and we end up reducing our copper. And so that copper at that point can dissolve into the electrolyte, and then we've got copper now floating around, which does the same thing. Creates dendrites, begins piercing the separator, and now we have a short circuit internally. And so while we may not have as much going because we over discharge, we still have just catastrophic failure of the battery. It's done. It can no longer, we've got a connection between the anode and cathode internally, and so there was no way to now charge the battery. It's over. So that's the end of it there. The chemistry really is about ion transport. It's about getting the lithium ion to move back and forth between a cathode and an anode to help the transport of electrons due to the reduction and oxidation reactions that can occur. And so if we don't have the chemicals, the chemical makeups of these film layers of our electrolytes just right, we have a lot of side reactions going on, degradation going on. And so not only do we lose ion transport, what we eventually lead to, if done at a high enough rate or a period of time or temperature, is this catastrophic failure. I mean, we create internal short circuits. We create internal gas pressures for causing explosions and sparks and bad things. And so one of my pieces of research that I did was even looking at changing these ionic liquids that we use, moving them over to creating polymerized ionic liquids. So can we create kind of a different type of synthetic material that would still be highly conductive of electron transport, but might be a little less reactive than lithium. To where if it was exposed to air or something of that nature, to water, that it's not immediately going to just burst into flames or explode. But polymers are most often, in a general sense, a short, fancy way to say plastic. And that's not always true, but plastic, good conductors of electricity? No. And so that's a big field of research, though, is can we create a polymerized ionic liquid that will somehow facilitate the same amount of electron transfer, even to a couple orders of magnitude. We're willing to give up a little bit there for safety. So, okay. Questions, comments, anything? And that's the end. All right. Wait. Anything? Yes, ma'am.
What are separators typically made of?
Just some membrane. I mean, just something that is thick enough to keep the electrodes from touching, but it's permeable for an ion. So, I mean, there's lots of materials. I don't really have an example other than it's just something that will allow for electron transport to cross between that. But it really is, in a lot of ways, just meant to be a physical barrier between the electrode and the cathode. Or, sorry, the anode and the cathode. Yep.
So I have a whole slew of questions from Amy.
Oh, no.
But since I'm going to pick up Chloe, I don't know if they've been asked.
Okay.
Or if you-
We can try. We can see if they've been asked or talked about.
And if they've been talked about, you could just tell me.
See the
that.
video.
Yeah, see the video. She said when we charge batteries from a wall outlet, do we have to convert the AC to DC?
No. That's usually part of the plug system. If necessary, that's usually, I mean, you would see that on the plug. Yeah.
She also asked, when and how would we apply an AC voltage perturbation to measure the impedance response?
I did not talk about that, and I would have to think about that.
You have to think of that, okay?
Yes.
What do we know about the texture or shape of porous electrodes?
Yes. So yes, see the video. No. So that's an issue that we talked about. To put this back up here, most of the electrodes on one side is a carbon, some type of carbon electrode, and then the cathode is typically a lithium-based, either ferrous oxide or a cobalt oxide, and so that's what we talked about. In that you can already see that if this gets too out of control, if this gets too thick, if something occurs where the reactions create more of this SEI, the solid electrolyte interface around a cathode, I mean, lithium ions are going to get stuck in here. They can get trapped. And so those we talked about through the different types of degradations and failures that would cause an increased thickness of either the cathode or the anode SEI that cause this lack of ion transport due to either impedance or quite literally that the lithium can't escape the material.
The rest of them, she asked you answered.
This picture?
Yeah.
Oh, awesome. That's why I picked that picture. Okay. Anything else? So the question was AC current versus an impedance? Yeah.
Yeah, I can read it back. So I don't miss over. When and how would we apply an AC voltage perturbation to measure the impedance response?
Yeah. Okay. That would be a good experiment. I'd have to think about that. I don't have an immediate answer. Sorry.
Okay, well, can we give our